Okay, so today we're going to talk. So last time we were talking about the quantitative, the two-flip angle quantitative T1 method. So here we'll start off with spiral scans, and there's not just spiral. There's a number of different methods of collecting data in K-space, and of which spiral is one. And to understand how spiral works, there really isn't a clear distinction between the readout and the phase encode in spiral. And so, but if you sort of think of this in the general, from the general perspective, is you've got to go to all different parts of K-space and collect data, and gradients, whether they're the readout gradient or the phase encode gradient or the partition gradient, they just move you to different parts of K-space. So if you think of it that way, then spiral makes sense. If you're thinking of it from the point of view of sort of the readout and phase encoding being frequency encoding and phase encoding being different, then spiral doesn't make any sense. But since we've long been thinking of it the correct way, then spiral will be very easy. So one of the things about spiral and non-sort of rectilinear methods of going through K-space is that they often use gradients that are smoothly changing. So a lot of times when we draw like a gradient, we draw something like this, like, the gradient is going along at a certain setting, which means like there's a certain amount of power going through the gradient coils to change the B0 field as a function of the Z component, for instance. And that's constant, and then there's a sudden change, and then it goes up to another flat plateau. So it turns out doing something like that is actually quite difficult for the gradient amplifiers. So it's even difficult. So we said, like a typical, if you draw the diagram for a typical amplifier, we think of an amplifier as like a transistor. We think of this one as the controller. So this is a small signal that we want to amplify, and here's the output of the amplifier. And then we have a large supply on this one. So the way an amplifier works is you have a small signal coming in here that we want to make into a really big signal. And so we have sort of a large supply of current here, and then this small one modulates this large one into this much larger signal. So that's like that's you would think of like a simple amplifier or just a transistor as doing something like that. So I mentioned last time that that's actually not the way. So that would be like a class A or a class AB amplifier. But we mentioned that the gradients have class D amplifiers. And what those do is they essentially approximate some smooth curve by just turning on and off basically using a transistor, the way like a transistor like this, but just using it like a switch, and just switching it on and off very rapidly, like at 100 kilohertz, 100,000 switches per second, and you approximate the waveform by these little pulses. Now, how do the pulses get smooth? That's a little complicated part. So it partly gets smoothed by the fact that the gradient coil itself has some dynamical properties when you put current in it. And so the effect coming out of the gradient coil is actually very smooth, even though what you put into it, you put these little pulses into it, But if you measure the magnetic field coming out of it, you don't see pulses because of the way that the current flows through a coil like that. One of the things, many of these things sort of interact with themselves. So if you start to put current through a coil, that's going to make a magnetic field, and then that magnetic field will affect the current you put into the coil. So there's like a feedback loop. So so this is the way the amplifiers work now, and so they can do something like this. They can do a better job of something like this, because you should be able to just like turn the amplifier off and then suddenly turn it all the way on. So you, in theory, could make something that sort of looks just like that. But it turns out, because of that feedback loop aspect, it's really hard to do something like this. So in fact, and what is the reason, which I was sort of beating around the bush, one of the problems are called eddy currents. And eddy currents are, sort of eddy is like a little whirlpool. So basically what happens is if you rapidly change the magnetic field and you've got some metal in there, you can induce currents in the metal. And those currents can then generate a magnetic field. And when they generate a magnetic field, it will have a tendency to oppose the magnetic field that is already there from, for instance, the B0. And so you can see something like eddy currents occurring is if I always demonstrated in the magnet, I have a little aluminum pie tin. And so if you take that piece of aluminum, it's filled with charges, and if you bring it close to the magnet and then try to move it close to the magnet, what happens is you're moving charges through a magnetic field. And that's one way of making a current. So if you move some charges through a magnetic field, the charges will move in that conductor. Or the opposite is if you move a magnetic field past a stationary conductor, the charges will start to move in the stationary conductor. It's the same situation either if you move the charges relative to the field or move the field relative to the charges. But when that happens, when you move those charges through the magnetic field, they start to rotate. Big current. It's low voltage, but a big current forms in that pie tin. It doesn't shock you or anything, but there's lots of current there. And then that current generates a magnetic field, and that magnetic field opposes the main magnetic field, the B0, that actually caused those charges to move in the first place. And so then you get like a little pushback. So if you stop pushing on it, there won't be any force. As soon as you move it, it generates, you cause charges to move, they make a magnetic field, that magnetic field is opposite to the main magnetic field, and you feel a push. So that's an example of eddy currents. That happens every time if you look at the magnet is like a giant, it's a big metal can. It's got tons of charges in it, and then it's got these, magnetic, it's got these superconducting loops around it, but it's a ton of metal. The magnet weighs 12 tons. So as soon as you change a magnetic field, like with a gradient, it immediately causes currents to flow around. And these eddy currents, and they flow around for kind of a long time, like 50 milliseconds, like a really long time. So the time constant for these things, so if you suddenly change the magnetic field, this current's all sloshing around, generating magnetic fields that are canceling the one thing you're trying to do. And so it turns out if you do something like this, what actually happens, so if I feed this signal into the amplifier, and the amplifier accurately generates a current that looks like that, what will happen is the current will be going up like this, and then I'll make it flat, but instead what will happen is it'll do something like that because of the eddy currents. And so if you want to get something that actually looks like that, you need to sort of like feed in something that is more like that. And then what will actually come out after the eddy currents do their thing is what you want. And so there's a whole calibration of the scanner for eddy current compensation that will translate what you said, what you want, into what you need to actually get what you want given the eddy currents. So why do I go through all this? Well, it turns out if you instead of feeding in something with sharp edges, feed in something that looks more like a sine wave, well, everybody's more happy. Everybody's more happy with a sine wave than things with sharp edges, and that's exactly what you have with spiral imaging. So with spiral imaging, the idea is we go through K-space. We go through K-space in a spiral type shape. So we'll go over how that works. So basically, the plan is you just turn on two gradients at the same time. So you turn on, nominally the phase encode gradient and the readout gradient at the exact same time. So this is an example of spiral EPI or spiral one shot 2D. So the idea is that we do an RF pulse. So we could do, say, a 90-degree RF pulse, and then we would do our regular sharp-edged slice select, because if we're doing a 2D slice, like that. But now here's our this is Z. Here's the Y, which would normally be the phase encode, and then here's the X, which would normally be the readout. So what we do now instead is, instead of really even having a formal echo, what we do is we just turn on both the phase encode gradient and the readout gradient at the same time. And so let's turn them on in sort of sinusoids that slowly get further and further apart like that. And then this guy, let's move this guy up to the top and then turn this guy slightly out of phase. So did I draw it sort of right? Yeah, not quite. Sort of right. And so what we want here, it's drawn correctly over here, but what we want is, we want a systematic offset of a quarter cycle. So this is, 1/4 cycle. Or, quadrature. So we want something that's like the relationship between a sine and a cosine. So a sine is just exactly like a cosine, but it's just, you could just think of it as shifted by a quarter of one cycle. So it's a little more complicated because we're changing the wave, we're changing the, the number of cycles per second here. But what happens if you do that? And so what do you get out of that? That's an important point. There's no like echo really. What happens is, so that there's an FID here, but then when you start a recording, what happens is you just get a whole bunch of signals, out of here the whole time. There's no echo per se. It's just like a continuous set of signals. So what are you actually doing? Well, if you think about it in K-space, what's going on is you have, and there's all different ways of doing it. The way I drew it here, we could draw it as starting from the center of K-space. So if you look at what the gradient is going to do at each point, since one of these is a quarter cycle away, what's going to happen is it will make you go through K-space like a spiral. And since the gradients, since the spacing between these oscillations is getting wider and wider, what that means is that you'll be going to further and further out in k-space. And so you'll sort of go around and around like this. So this one would be starting at the center of k-space and then, going out around k-space. So that's the spiral idea. And the way to think of it is that at any moment in time, the gradient, the integral of the gradient just tells you, where you are in k-space. And so, if you take one of these gradients, it's moving you further and further in the y direction, but then it reverses, and so then it starts moving you further and further in the minus y direction. And then meanwhile, this one is doing the same thing except in the x. So it'll be moving you in the x direction, but then eventually you'll cross over and it'll start moving you in the negative x direction. So, if you look at that spiral, it goes negative x, negative y, and then negative x, it goes x, negative x, and then y, negative y, and those are a quarter of a cycle out of phase. So that's a spiral. So it turns out the gradients like to do this, and this is easier to do for the eddy currents because the eddy currents are all kind of smoothed out. And so you still have to do eddy current compensation for spirals, because when you do the spiral, it's going to cause eddy currents. But in general, the magnet likes to do things like this, kind of little sloshy, sort of smooth changes. It doesn't like to sort of like zip to the corner of k-space. It would prefer to sort of like just sort of go there by a nice curve. So that's basically a spiral, and so you're collecting. So this is the RF, signal. So you basically just, as soon as you start up the gradients, you just continuously collect data. So there's no echo really. There's just like there's just a whole bunch of data through all of k-space. Now, one of the problems. So you're collecting data, so here's your data points. You're just collecting data as you go along. But one thing you might notice is it's not on a grid. And so one of the problems with spiral is that unless you want to do some completely arbitrary general linear inverse reconstruction, you generally have to sort of resample it back to a grid. And so what you do is you establish just a regular XY grid, and then you just figure out, you basically interpolate the data onto that grid. And so, typically you do some kind of what is just called regridding. And then once you've got it on a regular grid, then you just do Fourier transform. So, so if you just collect the data uniformly in time, you'll just end up with a bunch of samples along this spiral, and obviously that's not going to exactly land on a grid. So there's various different ways of doing this, and so one of the ways, I've got some equations in there, but I won't bother with the equation. We'll just sort of draw them out. So one thing you could do would be constant angular velocity. So if you did constant angular velocity, the gradients, the two gradients would look like something like this. So they would sort of get bigger and bigger, because if you want to sort of like make an even speed going around k-space, an even speed and angle, as you get further and further out, the actual local speed has to be faster through k-space, and so that means you need a bigger gradient. So this would be this would be like the gy and the gx gradient. They have to be some, and I wrote out the equations for how you can make something like that. So that would be constant angular velocity through k-space. And that's kind of a little funky because you end up going really fast through the outer part of k-space. But you could also do constant linear velocity. So just, go through the same speed through k-space. And if you look at what gradients you need for that, they're going to be like the ones I drew there, where they'll start sort of they'll suddenly ramp up to a big number and do something like that. They'll always be like a quarter cycle out of phase, but they'll look something like that. And so what do people do in practice? They usually do something sort of in between. They start off with constant linear velocity when when you're right in the middle of k-space. To make constant angular velocity, to make constant linear velocity is very difficult because you're going around so fast, it goes beyond what the gradients can do. So typically you do something that looks more like this. So you start off with constant angular velocity, and then you eventually end up at constant linear velocity. So you can see there's a whole bunch of little, practical. So this is mixed. Start. Yeah, so start constant angular, then then linear. And that's a more practical thing you can do with the gradients. So there's all different little fiddles. The other thing you can do is, one thing you might notice, if you start in the center of k-space, your echo time won't be very long. Your effective center of k-space, TE. So this guy is, effective. So TE effective, which means like, center k-space. Short, because we started in the center. And so one thing you can do instead would be, which is commonly done if you want to do functional MRI with spiral, is that you could basically start in the edge. So what you would do is the RF pulse would bring you to the center of k-space, and then you could go out, turn on both the x and the y gradient really strong. So you could do something like, turn on just like go to the corner of k-space, like that. So before you start, go all the way to the corner of k-space. And then, go around k-space and then come in. So this would be like like outside in spiral. And then what would happen is you'd go all the way around, and then eventually you would get to the middle, probably doing a reverse of this kind of setup. And then at the middle you would get the echo. Of course, there is no echo in the sense that you're just basically collecting data the whole time, but you would get the center of k-space to be late in the game, and so then your effective, so this is TE effective, center of k-space short, with in out. But this is out in. Or you could do both. So you could go, like in out in. That's a common thing you would do. So just start in the center, and then you have like a really big signal because there hasn't been any time for T2 star decay. Go all the way out and then come all the way back in, and then get a second one. In fact, spiral can go so fast that it's possible to you could go in and out like 6 times. So one of the things, because it's easier to do these kind of smooth movements of the gradients, one of the features of Spiral is that you can actually record really fast, and so you could get an image. In the case of people have optimized Spiral for imaging the actual sort of vocalization, like imaging the glottis, what's actually going on with vocalization, and in that case they've actually got it up to about 50 images per second, so 50 full collections of a K-space plane per second. So that's only 20 milliseconds per image, or something like that. Yeah, so you can go very fast with Spiral. So that's one of the advantages of it. There's other versions of this, and you can even extend it to 3D. So another example of something like this. So instead of doing Spiral, you could do like sort of like what I think of as like the 1950s atom picture. So instead of like making a spiral, what you could do is you could do something like this. Say go out here, and then do something that looks like sort of an atom like that. And I can't. There's a name for that. I think it petal or something. But you can. But so in this way you could go through the center of K-space multiple times. So that's another way of doing it in 2D. Yet another way of doing it in 2D is you could do something like you could just go through the center of K-space like that. And this was kind of by analogy with a CAT scan. And one of the guys who invented MRI, this is the way that he originally was doing MRI. It's not commonly done anymore, but because there's various distortion problems with it. But the idea is you sort of do something a little bit like echoplanar, like go out, so go across K-space and then come across K-space again this way, and then say move that way a little bit, and then come across K-space again that way, then move that way. So that way you would have a lot of samples of the middle of K-space. So that would be like a radial passage through K-space. So that we can still do that on the scanner if you want. And then there's another one. This one's called, we have this one on the scanner too. It's called, I think GE calls it propeller. Propeller, I think with an O. And then it's called Blade. On Siemens it's called Blade. And so the way this one works, yet another one, what we do is so here's K-space. We pick like a little chunk of K-space like that. So you go from the center of K-space and you go out here, and then you do something that's like echoplanar. That sort of goes like this. So we went this way, and then back that way, and then this way. So that's a blade. That's one blade, and then you collect another one that's maybe like over here. Let's kind of rotate it a little bit and do the same thing with that one. Go through the K-space again. So one advantage of this is that you go through K-space, you go through the center of K-space multiple times. And so what you can do is you can use that information to actually compensate for motion. So so this is a method this is a method, since you're going through K-space multiple times, you can measure where the head went using the center of K-space, and then effectively fix the data before you reconstruct the whole thing. So it's a method of, it's yet another method of sort of motion control. So, but my favorite one of all, before I get to the very last thing, is how would you collect the data the absolute fastest possible? And that would be a 3D 1950s atomic spiral. So the idea is you would do something like this. So here's our 3D K-space. So here's our 3D cube of K-space. And so here's the, we'll project in there's the center of K-space. So here's the back of the cube. Okay, so here's the center of K-space, and so here's the, say the Z direction and the Y direction. So this is not real space, it's spatial frequency space. And then what you do is you just do this kind of thing, except do it in 3D. So you would imagine you're kind of like sort of rotating around in three-dimensional K-space. This is like the absolute optimal super fast method of collecting data, because you got all three gradients on. So basically what you would do, you would turn on all three gradients and they'd all be oscillating at the same time to sort of like run you through K-space like that. And people did this once. They actually showed that it could work, but this would be the absolute fastest way of collecting 3D K-space. And so you might be able to go so fast that you could get over some of the motion artifacts with 3D EPI. So this is, one of these days somebody will sort of make an optimized version of this that would allow you to do basically probably TR like 500 millisecond or 250 millisecond full 3D images, so that you could collect like 4 images a second or 8 images a second. Now you're going so fast through K-space that the bandwidth is very high, meaning like the time between successive, the delta t over here, and the bandwidth, it just equals 1 over the delta t. So bandwidth would be high because it's 1 over it, meaning that delta t is small. So the signal to noise is lower when you go super fast. But if you're collecting if you're able to collect 8 volumes a second, you can make up for it by having more data. So, that's my favorite. One of these days somebody will make a practical one like that could potentially displace multiband because it's going so fast. And it's a 3D scan, so it's getting data from the entire, it gets the advantage of the signal to noise advantage of a 3D scan compared to a slice. So you can see there's all different ways of going through K-space. There's all different little tricky methods. And there's a whole sort of field of people who study spirals. And when we talk about, one of the things you might wonder, why don't people do spirals more often? One of the reasons is because they look a little blurry. So when we talk about, next time, when we talk about the Fourier shift theorem and B0 defects, we'll see that the effect of a B0 distortion for a echoplanar scan, sort of a standard rectilinear echoplanar scan, is just to cause a spatial shift. So the B0 defects cause spatial shifts. What happens, so the image looks sharp, but it gets distorted. So what happens in spiral is that a B0 defect causes blurring. The image is kind of geometrically accurate, but blurred. And in some respects, it's kind of better because it doesn't distort things. It just just blurs them a little bit. But people like sharp images, and so people in general have preferred a distorted but sharp image over a more veridical but blurred image. And so there's ways of fixing B0 defects, and there's ways of fixing it with Spiral. And so, like I said, eventually somebody will put this all together, and Spiral could become a lot more popular than it is right now. But right now, it's sort of not too many people do it. They may have heard of it, but they don't really sort of do it very commonly. And so I just wanted to finish up with a spiral scan. Now this is, the one I showed you was a gradient echo because there was no spin echo in it. But you can do spin echo spiral too. So that would be, you do a 90, do a 180, and then start turning the gradients on so that the same amount of time between the 90 and the 180, that amount of time later you go through the center of K-space. So you could do a spin echo spiral. And so what I want to talk about here is this is something that Eric Wong at UCSD showed me a number of years ago. And so it's a spiral 3D inversion recovery fast spin echo. Okay, so it's a 3D spiral that has inversion recovery, and it's doing it as a fast spin echo. So how does this work? This is just a very cool sequence. So the problem when we talked about MP Rage, the problem was it's like an inversion recovery. So we do an inversion recovery, we do an inversion, and then we wait a while, but then we suddenly start doing a bunch of alpha pulses until we get to the center of K-space, where hopefully here's the other more slowly recovering tissue reaches 0, so we get a big contrast at the center of K-space, and then we just continue doing this, non-steady state until we do the next one. And so we're collecting data during this whole time, but it's non-steady state. So it's non-steady state. So that means that the effective inversion time for different spatial frequencies is different. And so, you'll have like higher spatial frequencies somehow having a different contrast than lower spatial frequencies. It's kind of disturbing, a disturbing non-steady state scan. And so Eric Wong's idea was, why don't we do like a really good inversion recovery? And a good inversion recovery would be do an inversion and just wait until we're right exactly at that point, and then do 190. So here's a 180. So there's a 180, and so these are all the alpha pulses here, alpha, etc. So we're doing, those are all the fast gradient echo pulses. But now let's just do 190 here. So we do 190, and then once we've got 190, now we do a bunch of 180s in order to do fast spin echo. So this guy was, fast, gradient echo. So here we do a bunch of 180s. So this was a 180 and then a whole bunch of alphas. This is a 180. Wait until we're right exactly at the highest contrast, then do a 90, and now we've got a good signal that is essentially with a huge amount of contrast from the fact that we just did the 90 right at the appropriate time for an inversion recovery, and then we collect a bunch of 180s from it, all of which will have that same high contrast. There'll be a little T2 decay in them, but they'll have a very large longitudinal recovery contrasts that will be the same. And the problem is, of course, you're just waiting around a long time. Here we're collecting data. We just wait a little while and we collect data immediately. Here we're waiting around for a huge amount of time. But the advantage is that because we're doing spiral, we can go very fast. And so what does the whole cool sequence look like? So it looks like this. So we start off with a 180 over here. So that's our, and then we kind of wait a long time until we get to the center of K-space. And then when we get to the center, sorry, not the center of K-space, when we get to the point at which the two tissue types, where one of the tissue types that we want to null, sort of like turn to 0, is at 0, and the other guy is above 0. Then we do a 90, and then we do a slab. This is a 3D sequence, so we do a slab select. So this is slab. So not a slice, it's a whole volume. And now we just do a spin echo train, like a fast spin echo. So now, so this guy was the preparation. So this is the inversion time right here, TI. Now we do the 90 right when we get the most contrast, and then we try to get as many echoes out of that as possible by doing 180s. And so now here's a 180. And so this is a slab select, so we've got to do one of those funny things with ears on it. So it's got a little ear like that, and then slab select, and then because a 180 occurred, the canceller looks the opposite. But this is a 3D scan, so what we're going to do is we're going to pile on top of this ear, we'll pile on top of it a set of partitions like that. So here's all those partitions. So we'll pile that on top of the ear to save time. And then, so this is the GC, so RF. Okay, so now we got to do our spiral. And so the spiral will be on the y and the z gradient. So what this is, the y and the x gradient. So what this is a stack of spirals. So what does that mean? So this means it's a, so you can think of this as, in one dimension we're doing spirals, but in the other dimension we're just doing planes. So here's the center of K-space right here. So what we can imagine is, let's just take, if we turn on a particular partition phase encode, that will move us up to a particular part of K-space. So say we're over here, and we're up over the, say this was the 0 axis, the 0 axis of K-space. Here's a little higher spiral. And then what we can do is, spiral around that. So like spiral around this, like that. But turns out we can't quite collect enough data, and so we have to do an interleaved spiral. So that means like one of these pulses will do that, and the next pulse will sort of like get some of the data that's in between. So it's a spiral 3D inversion recovery fast spin echo with interleaved spirals. So we can collect some of the, because we can't quite collect all the data in just one pass through K-space, can't get enough echoes, too much deposition of RF. And so then what you do is, on a different partition, you go to a different part. The way I drew it out here, this was the KZ axis, because we're, and then this would be like the K, say K X and KY. So this is a stack of spirals, stack of interleaved spirals. And so what does that look like over here? Well, then we have to sort of do our spiral. So here's our spiral readout. So we quickly do like an echoplanar type, spiral readout. And then we have to sort of like fix things, wherever we ended up, like go back to the center again. And then that amount of time later, do another 180. And now this time, when we do this 180, we have to fix this guy. So here we're fixing this guy. So this if this time we went up, this time we go down to sort of, because it's a fast spin echo, we're saving all the signal, so we have to sort of put everything back. And then we do our slice select, and then when we're on the other side, we tack on another pass, going this direction. So, and then collect another spiral. So you can see it's very optimized to collect the data. So you could collect 16 or 32, 32 of these. So you could say, do 16 interleaves, for instance, so only collect 1/16 of data for each of these spirals. And then, so you have to interleave, and then you have to do all the different partitions. But the end result was just a staggering amount of contrast. So this was set up to give T1 contrast. So normally in T1 contrast, if you look at a MP Rage, you might have, say, the gray matter. Gray matter might be, say, 95, and the white matter might be, say, 115, something like that, or say 120. So, you might have 20% contrast, 15% contrast. It's a relatively small contrast. So this would be like an MP Rage. So what did the contrast look like here? It's just stunning contrast. The signal was a signed signal, so it came out something like, white matter equals 200, gray matter equals 0. The cerebrospinal fluid, equals negative 80. I mean, it was just like unbelievable contrast. When I looked at the image, I couldn't see the gray matter. The gray matter was so dark relative to the white matter, it looked like there was no gray matter. But, when I turned it up, I could see. And why is that? That's because we really wiped out the gray matter signal here, because the signal all comes from a 90 done when the gray matter truly was at 0. And so it's possible to get like contrast that's like, 5-10 times as much as our standard scans. Now, have people done this? Nah, they didn't do it because they looked a little blurry. They got a little upset because they looked a little blurry, which, we could eventually fix. But this shows you that, there's still opportunity for innovation and use of tricky new sequences in MRI. So I'll just leave it with that. There's probably a publication on this, but nobody, like I said, nobody's really used it. We don't have this sequence yet on our scanner, but maybe I'll, since UCSD is buying Siemens scanners, perhaps we'll have it in the future. Okay, I think we'll end the recording there, David.